So, hello everyone. I would kindly ask you to take your seat so that we can start with the next session of various speakers that will be contributing in the next session. We will start with a colleague, Henriette Bier, who is coming from Technical University of Delft. She is leader of a robotic production lab at TU Delft. She is trained as an architect, has also worked with Morphosis in her career as architect, and after that she has been very active in academic community in the field of robotic design and digitally supported architecture. She has collaborated with numerous institutions such as MIT and ETH Zurich and has published several works on cyber-physical architecture. She has been leading numerous research projects, also EU projects, so we're looking forward to your lecture. The floor is yours.
Thank you very much for the introduction, and thank you for inviting me to present here my work. I'm going to present work on computational design and robotics in what we call more recently cyber-physical architecture. Cyber-physical architecture is actually also a journal. We have now the 5th issue that has been published, is available online, and it has been co-edited with Michael Hensel, who is professor here. Unfortunately, he's not today here, but we have worked together on this issue on interdisciplinary data integrated approaches, which, as mentioned before, is available online. I invite everybody who is interested in these kind of topics to have a look and download the issue. And I move on with presenting the work that we are implementing in the Robotic Building Lab. So the work focuses on robotic systems that are integrated into physically built environments, but also into building processes. And how do we implement this work? By developing designed robotic production, assembly, and operation methods. I'm going to explain what they are in the following slides. And I will start with designed robotic production. We have a robotic arm linked to a parametric model and with an end effector. And the end effector can be customized. So in the first test, we implemented additive manufacturing using ceramic clay, and we customized the end effector. As you can see here, we customized also the material, and we designed a very specific material, as you are going to see in this movie. The project is titled Scalable Porosity. For some reason, the audio doesn't work again, but I think it's fine also without. So this was the first experiment. You can see here a movie where we used as end effector a light, and the translation of the computational model into robotic paths was the first step, and then working with the material. In this case, you see 3D printing with ceramic clay on a double curved surface. We just tested at the beginning various possibilities to work with this technique. And we usually have an overall design then from which we take a fragment, we structurally optimize it, and generate, in this case, a cellular pattern based on Voronoi, and we do that according to the structural analysis in order to reduce material and also increase speed of production. So here you see a continuous 3D printing path of this Voronoi-based material design. And at the time, we looked only at the structural analysis and created the structure, as mentioned before, using less material and being faster in the production process. However, we had intuitively thought that it may have also insulation properties, which later on this year actually we have proven indeed to be the case in another project. The same, let's say, Voronoi-based material design we implemented in another project where we tested basically variable stiffness, meaning that we distributed the material throughout this chaise longue in such a way that it has parts that are more stiff and other parts that are more flexible. Again, as mentioned before, we used the structural analysis method and a Voronoi-based approach. We worked together with an industrial partner from Rotterdam, 3D robot printing, and we used TPE. And as mentioned, the title is Variable Stiffness. And we use usually Grasshopper scripts and various plugins for implementing our designs. And we work usually with students who are testing these ideas on smaller scale, and then with PhD students who are, and researchers who are pushing basically the research development further. Here you see the variable distribution of material and a test at 1-to-1 scale implemented in about 30 hours, and the assumption with respect to the variable stiffness has been proven. However, as mentioned before, this is the first prototype. We continued with additive manufacturing, but we also looked into subtractive manufacturing. So our ambition is that in due time, we cover, so to say, all construction tasks, if possible. But of course, not only us. Several groups over the world are looking into these techniques. And we know that 50% of all tasks can be automated, while 45% approximately, of course, are going to be human-robot interaction supported, and only 5% are going to remain in our hands. So this is, so to say, the step where we looked into the relationship between additive and subtractive, and a master's student thesis looked into developing this atrium, and we took this to the next level. You see the optimization, the members are accordingly designed. We take a fragment, and in this case we used circular wood. And we have here an optimization routine for the node. And this node is 3D printed with a technology developed at TU Delft, not in our lab, but in the mechanical engineering lab. And this is still work in progress. This is the system that they have. And of course, the challenge is to 3D print without support, which again can be implemented by using computational methods. As mentioned before, we used circular wood. This was a collaboration with the Faculty of Architecture in Amsterdam, and we glued pieces of wood together, and then this is, as mentioned before, a fragment from the previous structure that I showed, and we milled this fragment out, and we were positively, let's say, surprised how beautiful actually this material becomes when milled in this shape. However, also this project is still work in progress, and what we realized was that we create still dust. So how the circular wood approach is incomplete. So what do we do with the sawdust? We decided to 3D print with sawdust, and we developed another project which is using a wood-based polymer. Is implemented, this project, in collaboration with a landscape architect, and we titled it Biocyber Physical Planetoid. It's basically a 80 centimeters in diameter structure that has a cavernous, let's say, it's a cavernous structure, allowing placement of a earth piece with seeds, and it's supposed to be placed, the structure, in leftover spaces in urban environments to rediversify the respective area. It has also sensor actuators in order to monitor the microclimate and invite passers-by, but also neighbors, to take care of the plants. So it has been scientifically proven that engaging with plants and taking care of plants is healing for humans. And the theory was that this would be a way to engage them also in these activities. One of the challenges, of course, is when you are scaling up is how to, because 3D printing, basically, you can, to a certain size, implement in the lab, but then how do you scale up? You develop components that need to be assembled. So in this case, we had, I think there are 5 components that can be assembled together. And as mentioned before, the scaling up is the real challenge. Students looked into the possibility of scaling up of this planetoid towards generating even a larger structure that could be populated by animals and plants, but also could offer humans spaces to climb, relax, etc. Continuing looking into the scaling up question, in a project implemented with the European Space Agency, we proposed the building of a habitat on Mars using rovers. So again, robotic production, of course, on Mars, that's what you have to do, you have no other option. And we used these rovers that were developed in Delft and 3D printed with the technology of a firm in Eindhoven using, actually, in this case, concrete. And we replaced the concrete with regolith simulant. So regolith is available on Mars. And we 3D printed with this technology that they have there available. And again, we used the same material logic. And in this project, we proved, as you can see here is, for instance, the digital model next to the 3D printed prototype. You start to modify the model based on what you learn from the material experiments. So it's always a feedback loop between the two. And in this case, we did indeed also material testing, and it is, in terms of strength and also in terms of insulation property, exceeds even the capabilities of concrete available on Earth. So again, with students, we looked into the architectural aspects. They tried to integrate functional requirements, in this case, furniture, plants, etc., into this Voronoi-based geometry. And again, we use with this point cloud in order to distribute the Voronois depending on the function, structure, and environmental requirements. The componential logic was based on the assembly requirements. And again, we have the computational model, then we have the robotic paths and the printed prototype, and then the assembly. The assembly we implemented as human-robot interaction approach in collaboration with the mechanical engineering in Delft. And you see here the process of teaching the robot to handle these components. This is a short movie showing the work that we implemented, location. We used the kite system to generate energy. We used rovers and robotic approaches. This is the overall geometry that we implemented. We 3D printed a couple of components about 50 centimeter in height, and we tested the idea of how these components could be assembled. As you can see, we have a structural analysis, then a distribution of Voronoi based on various aspects as mentioned before. And then we took this fragment, and this fragment was built from 3 components. And here you see the human-robot interaction-based assembly. So the robotic arm is controlled by voice commands. I'm not sure if you can hear, but basically he's saying down, for instance, or so various commands. So in principle, this can be implemented. We didn't implement it yet with the real components. This, as you have seen, are basically cardboard components. So the real components are much heavier. These kind of robots have some constraints with respect to weight. So it's still working in progress, but European Space Agency is interested in co-financing a PhD student to continue working on this project. So now I kind of covered the design robotic production and assembly. I move on now to design to robotic operation, which focuses on integrating robotic systems into the built environment. So the students were exploring the idea of an adaptive or responding facade that would, so to say, have a system that would open and close depending on the human's movement and environmental conditions. And the students used a Kinect system connected to their computational model. And these ideas we have been implementing for a while now. In this case, for instance, we implemented interactive lighting for a podium for a conference at TU Delft, and the lighting was responding to the various speakers, to also the sensors that would basically collect data from the speakers and the environment, and the light would change in intensity and color. Here you see 3 speakers, and depending on how they would behave, the colors would change. Another project where we again looked into interactivity, but at this time at, let's say, urban scale or larger scale. The students proposed using drones for, let's say, an exhibit in Rotterdam, where they would guide visitors, but also would create structures, temporary structures. And the idea was that the drones basically would create these structures and would also basically remove the structures depending on requirements. This is an impression how the students imagined this could be implemented. The structure would be, of course, stable only when the last drones would connect. And they also built a small prototype for fun to test the idea. Yeah, design to robotic assembly, I already introduce, but using human-robot interaction. This was actually a previous project before we did human-robot interaction. We implemented it in Germany, Dessau Institute of Architecture, and this is the first time when we realized that, okay, we need to look into human-robot interaction, because if you want to have, and you need to have basically humans working next to the robot, then you need to have a safer approach. In this case, the robotic arm was placing linear elements of various size, and this was also part of a larger structure, architectural structure, that was not built completely, just the fragment was built. So one of the major challenges is basically the integration of all this. So basically, if you have Design-to-Robotic-Production, you integrate this with the assembly and then to operation. This is obviously a big challenge. One of the students who attempted at some level of integration was proposing a structure built in the North Sea on an abandoned rig. So we know that they're going to be abandoned. The question is, how are you going to repurpose them? So he used an agent-based modeling approach to generate a multifunctional structure, and used also differential growth to create units. One unit he developed in more detail. Here you can see basically the generation of the unit and the stairs within the new unit. And here all these Voronoi-based elements represent openings such as windows or climate control components that we also 3D printed, and the 3D printing process we implemented not only with respect to the materialization, but also with respect to the development of the 3D printing system. So the system that you can see here, we designed and also produced. So hence, we design not only the architecture, but also the tools that are needed for that. And maybe a last couple of slides that talk about these attempts for integrating all these aspects is a project presenting urban furniture. And usually the overall design is driven, as mentioned before, by respective user and functions that are distributed, in this case, along a path. This is a pavilion next to the water. And we looked not only into generating the architectural design, but also the design of the interactive system, which in this case was again about lighting that would respond to the number of people who are there and activities that are there. All these projects that I'm showing now in very short go usually through various steps of evolution, as you can see here. Here there are 4. On the right-hand side is the last version, and usually from this last version, that in this case is also 3D printed at scale, we take a fragment and we prototype one-to-one. So this is basically the usual workflow. And these projects are presented not only in the spool issues that are available, but also in the book Robotic Building in Springer, that in this case it has a chapter, open access, that I invite you to have a look in case you're interested. So I kept it a little bit short because I was thinking it would be interesting to have a more interactive, perhaps session at the end, so I'm open to answer questions.
Thank you very much for this very impressive lecture and work that you have been doing with your students, addressing many fields actually of architecture and civil engineering. I'm sure we have questions, as in our special research area project we have many areas that address actually the topics that you have been mentioned, like human-robotic interaction, for example. So we are open for questions if there are some. Yes, please.
Thanks for this very nice talk. Sorry. So in many of your projects, you use these Voronoi type structures. Is there a special reason for that? Could you comment on this?
Yes, there's a special reason. We can control the distribution of Voronoi. So meaning that not only the distribution, but also the shape of the Voronoi. So these kind of Voronoi-based structures can be designed at all scales, material, component, and building scale. So this is why we work with Voronoi. In terms of the, let's say, overall shape, now Bill was talking about the differentiation between topology, shape, and size. In terms of shape, we have not explored enough, the way I see it, its potential. So we focus more on performance. But I think it has a lot of potential also in terms of freedom of shape. So at the moment it seems a bit too literal, I think, the way it's presented, in the sense that the Voronoi is very obvious. But I think depending on how you design with it, you can, there's a freedom that we didn't develop yet. This is what I try to say.
Thank you. Are there some further questions? So, yes, please.
I have a question about building on the Mars. So how would you create a liquid material on the Mars to create these 3D printed buildings?
Well, to my surprise, I have to say, talking about Mars, it's a bit challenging. So I have to say, I was very reluctant at the beginning to engage in such an attempt, but my students were very, very eager to do that, so I helped them to formulate the first idea, and European Space Agency found it interesting. So this is how we got into it. So still, we are working on that maybe a year and a half, two, approximately. So I'm not an expert, but what we know so far is that the materials that we proposed can be found on Mars. And so basically we could 3D print with them. We concluded though that we would not use a cement-based approach as we proposed, but we would move towards using other materials. So, but this is work in progress. But in any case, always when you propose something for Mars, it has to be materials that you find there. But I have to say, I'm surprised. It's quite there's a quite vast, let's say, palette of materials. So in the sense that I didn't feel as constrained as I thought at the beginning I would.
Thank you. So we have another question in the back. Maybe if you could briefly introduce yourself so that we just know the background from which you're coming and the motivation.
Oh yeah, sorry. I'm engineer turned robotician, but I'm doing mathematics from engineering robotics background. So my question was, what is the way to look forward to communicate between, or fill the gap between engineers, geometricians, and mathematics when we are using robots? I mean, what is the missing element? It's very hard to communicate, right? When you're communicating with mathematicians and geometricians and engineers, can you comment on this?
Yes. So I have to say I was fortunate so far, in the sense that all roboticists I worked with, also all computer scientists I worked with, we were able to communicate with each other. But I assume it has also to with the fact that, in principle, at least, and they were also saying, they were involved also with my students, and they were saying that from all architecture students that they encountered so far, my students were the most basically open and capable of engaging in dialogues with them. So I think if you, for instance, as an architect, I speak now from my perspective, if you are fascinated with these topics and you start working on them, then as an architect, in principle, you always work with other people, because building let's say, such a building like this one or any other, it's impossible to do by yourself. So basically you work with other people together. So architects are trained in principle to be able to talk with people of various backgrounds. It is a challenge, but let's say my experience was positive. So I can only encourage everybody to try to do that, also amongst others, because it's clear this is the future. So, and I have the feeling that architects are a bit slow in picking up this, these developments.
Thank you. I would like to continue in this direction as these people issues have been addressed. So you have mentioned that there is a prediction that 55% of building production will be completely automated. 45%, I think it's a human-robotic interaction, if I'm not mistaken, and only 5% it's in our hand, no matter who we are, if architects or engineers. So how would you comment on that? Because what does this mean for our profession, for architecture, engineering and construction? Because there is a big skepticism in the practice towards digital tools, and in particular robotic production, also fear that our profession, our trade will be taken away from us, and how does this reflect upon build quality and architecture in general? So this is this skepticism maybe, and why architects have been potentially slow to adapt and accept new technologies. Very similar fear is also present in construction, but also in industrial production. So there's a lot of research going on human-robotic interaction, in particular in industrial production. But how would you reflect that? What will be the consequences? Or how do you see that our profession will develop in the future, seen in this light? Or what will remain in our hand?
Well, based on current research and estimates, basically what remains in human hand is basically decision-making, so to say, what also at the moment is in our hands. So maybe just for a simple example, when I started studying, at least, we were drawing basically with ink pens manually. So, and the first computer system that I used, it was slower. The drawings were didn't look good. So basically it took me longer to go through the process than to not use a computer. Of course, meanwhile, let's say, the systems have changed enormously. So I like to compare it with that. Or basically even if you compare it with having a mobile system, a mobile phone, or we didn't have them for a while. And when we start to have them, we cannot live without them anymore. So basically what I'm seeing here is a fear that is, maybe it was also at the time when cars were introduced. So, or any new technologies that is introduced is for a time creating a sense of insecurity, because the future seems unpredictable, but in principle I see this as an opportunity, definitely, that we should embrace, amongst others, because it's unavoidable. So
do you think that we have sufficient decision-making tools then? Because you said our main area now, but in the future in particular, will be decision-making as designers, as architects, as engineers. So for this we need basically decision-making instruments. So do you think that currently we have enough of them, or this is the way to go?
well, we develop them. At least that's the way I see it. And I think also the symposium is about that, at least. So basically we develop those tools that help us. We saw also in the previous presentation, basically, you can help yourself to make informed decisions about use of materials, about use of structures. So I see this technology as just helping us in this decision making. But finally, in the end, we are the ones who are making decisions.
Do we still have comments? Yes.
Thank you again for your lecture. My background is in architecture and software engineering, and I was wondering, you presented the structural aspect of built structures, but very often there is building services like ventilation, heating, air conditioning, and those elements tend to make really beautiful designs rather, let's say, ugly from the point of view of an architect. Have you any plans to integrate building services in your designs in the future?
Yes, actually we did 2 studies already about this integration. I didn't present it here, but at the moment this is the focus, basically. So those studies are really preliminary studies with respect to how can be those systems can be integrated indeed in the components or layered on top. So those are the 2 obvious solutions. But yeah, we are working on it.
Thank you.
Okay, we have 2 questions in the back. One is the last row, and then after that, the 3rd row in the back.
Hi, thanks a lot for the talk. My background is in graphics and digital fabrication, and I was very curious after seeing the talk about the new fabrication techniques, especially additive manufacturing techniques. My question is are these tools developed in-house in the lab, or are there like collaborations with different groups and companies around? Like for instance, the sawdust fabrication tool or the silicon mixing tool. It was very inspiring to see new technologies coming to further.
Yes, thank you. Some of the projects are, so for instance, the silicon printing project, we did it by ourselves. But by the time we already had some experience that we developed also with others. So there are moments where we work together with others and moments where we are working by ourselves. But always, so to say, the knowledge, of course, that you develop is integrated. So I would say in all those projects, at some level, we had some expertise that was not, let's say, from us, but basically integrated from others. So we work with industrial partners, but also with colleagues from other faculties. So, and those are definitely important moments where also the learning curve is increasing.
Okay, and there was another question in the back.
Hi, my name is Emanuel Fonach. I'm researching here at the newly founded VR group, but with a strong background in using robotics at least. I saw a lot in your talk about using the robotic arms, different robotic arms. And I wonder, so usually these arms have some dead zones. Did you encounter any problems with that during the manufacturing process? Or do you have any solutions for that?
Yeah, we usually work with the constraints. We integrate the constraints in the design approach. Okay. So basically, also 3D printing without support, meaning that the maximum angle is 45. it's for us, it's basically a means. We just integrate those as constraints.
Okay.
So, but we, of course, we didn't look yet, and I think this is a challenge also for not only us, but for the whole industry, what it implies basically to scale up at building scale. Of course, it needs to still be investigated.
Yeah, this would be, thank you. This would be my follow-up question. Is there a problem with, what are the problems to expect with scaling up this to a like human housing scale?
Yeah, well, basically there are several, but maybe should mentioning a couple of those is, and we are going to look into that. So basically, if you, for instance, you need to look into how do you work, basically. Are you going to scale up vertically, or do you prefer to stay, let's say, horizontally? And what are the constraints with each of them? And then, so basically, it's a lot to work on. So we are going to, in the next couple of, let's say, months, look into the challenges for building vertically versus horizontally. Also prefabricating versus working on site. And then also the integration into components, as mentioned before, of also other, let's say, electrical wiring, water piping, etc., what is needed. So already this is a lot. So we have a lot of work ahead, but I think this is the beauty of it.
Yeah, yeah. Thank you.
Yeah.
Great. We have time for last question.
Thank you so much. Hello, I'm an architect and doctoral student from Budapest, and I would like to ask about the psychological aspect of this project, because you mentioned architects are a bit slow in catching up with the techniques, but I believe this is also because of our human features. We are quite hard on changing our habits and getting used to new things. And so do you think this is going to be a structure that is going to be familiar for people to live in or to use it as something to, as you know, our general life environment later on? Or do you research that as well?
As I mentioned this before, we didn't look yet into, let's say, those aspects enough. But I'm sure they can be addressed easily. In principle, considering that these are parametric models, hence I'm confident that they can be customized to various needs. We didn't work with users yet, for instance. So there are many layers that are not yet considered, because, of course, you have to choose basically what you focus on. But yes, I totally agree. This is something that needs to be studied. However, as I was saying, in terms of geometry, to go back to geometry, I don't see any constraints, let's say, that cannot be integrated as parameters and worked with.
Thank you.
Thank you very much for your very interesting lecture and also intense discussion. And we really hope to be able to talk with you today more on these topics. Thank you very much.
Thank you.